Hi everyone. In this session we discuss about Nyquist plots. Usually you might have discussed about the Nyquist plots. To draw the Nyquist plot we use some contour methods. In several books you might have referred. But here today in this session I am going to discuss how to draw the Nyquist plot in a very simple way, that is using polar plots. You are all aware that how to draw the polar plot. Usually we write for the given transfer function, we write magnitude and phase equations. From these two, we substitute omega equal to 0 and omega equal to infinite. At this, we will get magnitude as well as phase. And from this, we draw the polar plot. Once if you will be able to draw the polar plot, from the polar plot, we can draw the Nyquist plot in a very easier way. Let us see how to draw the Nyquist plot from polar plot. First of all, let us see what is a Nyquist plot. What is the purpose of drawing this Nyquist plot? This is one of the stability analysis techniques we use. We have a polar plot, Nyquist plot and board plot. These are the three frequency domain techniques. Coming to the Nyquist plot, using this plot, how to find the stability of a system? For that, we have some Nyquist stability condition or Nyquist criterion we can say. That says n is equal to p minus z, where n represents number of n settlements of J0 point. Number of n settlements of minus 1 plus J0 point. If it is in clockwise, it will be considered as negative. If it is in anti-clockwise, that will be considered as positive. And here P is number of open loop poles in RHS of the S-plane. Number of open loop poles in RHS of the S-plane. Come to the Z value, that gives number of closed loop zeros in RHS of the S-plane. N represents number of unsettlements of minus 1 J0 point. P represents number of open loop poles in RHS of the S-plane. Z represents number of closed loop zeros in RHS of the S-plane. Okay. The system is said to be stable only when the number of open loop poles is equal to number of n settlements of minus 1 J0 point. That means the closed loop system is said to be stable only when z equal to 0. When do you get z equal to 0? If n equal to p. What is n? Number of n settlements of J0 point. P, number of open loop poles in RHS of the S-plane. When these two are equal, obviously z becomes 0. If z is equals to 0, then we can say the closed loop system is stable. That is the Nyquist stability condition. Let us solve one example. We draw the Nyquist plot and test for its stability in drawing the polar plot. From the polar plot, we draw the Nyquist plot. Let us consider one example. The given open loop transfer function g of s h of s is equals to s plus 2 by s plus 1 into s plus 3. Some example. For this, first let us draw the polar plot, I said. So write the magnitude equation and phase equation. So what is the magnitude equation for this? Square root of omega square plus 4 by square root of omega square plus 1 into omega square plus 9. Let us solve one problem. So given transfer function, open loop transfer function is given as 1 by s into s plus 1 into 2s plus 1. This is the open loop transfer function given. So for this, let us draw the Nyquist plot. First, You know the procedure for polar plot. First write the magnitude equation and phase equation. From the magnitude equation for this given transfer function is omega into square root of 1 plus omega square into 1 plus 4 omega square. This is the magnitude equation. Come to the phase equation. Phi is equals to, for 1 by s, that is minus 90 minus tan inverse of, for this omega minus tan inverse of 2 omega. This is the phase equation. Now, let us substitute omega equal to 0 first and then omega equal to infinite. At omega equal to 0, what is the magnitude? 1 by 0, that becomes infinite. So magnitude is equals to infinite and phase is, this is minus 90, 0, 0. So that becomes minus 90 degrees. Next, at omega equal to infinite, what is the magnitude? That is 0 and come to the phase minus 90, tan inverse infinity 90, tan inverse infinity 90. So it becomes minus 270. So this is the magnitude at omega equal to 0 and this is the magnitude at omega equal to infinite. Now let me draw the polar plot for this. This is the S plane. So initially at omega equal to 0, magnitude is infinite and angle is minus 90. So this is the minus 90 axis. This is 0, this is 180 and this is minus 270 degrees axis. First for omega equal to 0, we have magnitude is infinite along with minus 90 degrees axis. So the plot comes like this. As omega increases, the magnitude decreases and finally the magnitude becomes 0 with minus 270 degrees axis. Magnitude becomes 0 with minus 270 degrees axis. So this is the polar plot. I think all of you are familiar up to this point. After the polar plot, we can get the Nyquist plot simply by drawing its mirror image. Suppose if you place a mirror here, how does it looks in mirror? So just it looks like this, right? When you place a mirror here, wherever it terminates, from there it starts and it goes in this way. Now we can get the Nyquist plot just by joining the mirror image and the polar plot in clockwise direction. Listen carefully. The mirror image of the polar plot must be joined with the original polar plot in clockwise direction. Like this. So like this you join here. Now this is the Nyquist plot for the given transfer function 1 by s into s plus 1 into 2s plus 1. After drawing this Nyquist plot, now we can test for stability of the system. What is the condition for stability of a system? Already we discussed n equal to p minus z. What is n? That is number of encirclements of j0 point. Now let us see whether this minus 1 plus j0 point is inside this circle or out of the circle. To know that, first we must find this value. What is the magnitude here? That point we need to find. Now, let us find this value. To find this particular value, where does it crosses the plot? See, it crosses the real axis, negative real axis. On the negative real axis, what is the angle? Minus 180 degrees. So let us equate this phase to minus 180 and solve this equation for omega. Minus 90 minus tan inverse omega minus tan inverse 2 omega is equal to minus 180. Equate the phase to minus 180, that is on the real axis. So when you equate this and solve for omega, then we get omega is equals to 0.707 radians per second. Now let us find the magnitude at this particular omega value. We know the magnitude formula. M is equals to 1 by omega into square root of 1 plus omega square into square root of 1 plus 4 omega square. Substitute omega equal to 0.707 here. Then we get magnitude is equals to 0.606. 0.606. Where is that point? If this is the 0.606, then where will be having 1? Obviously, 1 will be out of this encirclement, because its value is 0.606. Then where do we have that -1 J0 point? Obviously, 1 means it is more than this 0.607. Let us say here. So from this, what are the number of encirclements of -1 J0 point? -1 is out of these encirclements, closed path, closed contour. So there are no encirclements of -1 J0 point. So then n equal to 0. And from the given transfer function, that is 1 by s into s plus 1 into 2s plus 1. What is p value? P means number of open loop poles in RHS of the S plane. But here what are the location of poles? S equal to 0, S equal to -1, S equal to -0.5. There are no poles in RHS of the S plane. So P is equal to 0. Then what is the Nyquist criterion? We have a Nyquist condition, that is n equal to P minus Z. N is 0, P is 0. Then what will be the value of Z? Z is also becomes 0. If Z equal to 0 means what it says, the closed loop system is stable. As P equal to 0, open loop system is also stable. By drawing this Nyquist plot, we can say as the Z equal to 0, the system is absolutely stable. Even the closed loop system is also absolutely stable. Is it clear? So this is the Nyquist plot. Simply, we draw the polar plot, draw its mirror image, and then join these two in clockwise direction. Then we get Nyquist plot. After drawing the Nyquist plot, apply this Nyquist stability condition n equal to P minus Z. In order to know that, we must find the magnitude at this rail axis crossing point. First, let us find the frequency at this crossing point by equating the phase to -180 degrees. After getting that omega value, substitute that omega in magnitude, find the magnitude value. If it is greater than 1, then it means encirclements are there. If it is less than 1, there are no encirclements. Okay, please remember this. Then we can find the gain margin as well as phase margin also using this Nyquist plot. We know the formula for gain margin is equals to 20 log of 1 by magnitude at omega equal to omega PC. Omega PC means phase crossover frequency. Already we got phase crossover frequency. We have obtained the phase crossover frequency, that is 0.707 radians per second, and that we have substituted in magnitude also. We got the magnitude at phase crossover frequency is 0.606. So gain margin is equals to 20 log of 1 by 0.606. For this we get 3.71 dBs. This is the gain margin. And coming to the phase margin is equals to 180 plus 5GC. What is 5GC? That is gain crossover, the phase at gain crossover frequency. First we have to find the gain crossover frequency. That is, how do we get the gain crossover frequency? That means the frequency at which magnitude plot crosses the 0 dB line, or the frequency at which magnitude is unity. We know the magnitude equation, that is 1 by omega into square root of 1 plus omega square into 1 plus 4 omega square. This is the magnitude, and equate it to 1, solve for omega value. If you solve this on trial and error basis, then we may get omega is equals to 0.574 radians per second. Okay, so this is the omega GC, that means gain crossover frequency. Now, phase margin is equals to 180 plus 5GC. We know the phi equation. Phi is equal to -90 minus tan inverse of omega minus tan inverse of omega. So in this phi equation, let us substitute omega equal to omega gc, that is 0.574. After substituting this omega gc here, and finally the phase margin can be obtained by 180 plus 5 gc. So this we get 11.57 degrees. 11.57 degrees is the phase margin, and here 3.7 degrees is the gain margin. So we have drawn the Nyquist plot for the given transfer function. From that we have obtained the stability of this system, whether the system is stable or not. We got it. The given system is absolutely stable, and from that we got the gain margin as well as phase margin. So this completes a frequency response or frequency domain analysis of a given transfer function 1 by s into 1 plus s into 2s plus 1. Okay. Thank you.